So what we're talking about is streamlines and path lines. All right, and they are identical in steady state flow. So for our purposes, a streamline and a path line is the same thing. I gave two different definitions there, but they're the same thing. And a stream function is a function that defines streamlines. So what we've been trying to do is determine the pressure or potential field, and we created an equation for that. Then we used Darcy's law and the potential. We took the derivative of potential with respect to distance, and we got Darcy's law, and that was velocity field. So now we got the potential field and the velocity field. And then we want one last thing is the streamlines or stream functions. Okay, and think of a streamline as being the curve in space that a particle travels. And so if you had some sort of rock grain over here, and you had a particle in your water or oil, and it was flowing around over here, it would flow around it, and it would follow these types of streamlines. Stream functions are constant along streamlines. So what we learned last time, and I know we derived it by hand. I can't remember if we went through the PowerPoint notes, but what we said is that the stream function is a function of x and y. It's not a function of time. Okay, so that if it's not a function of time, then the derivative of the stream function with respect to time is 0. That's what that's what it means as not being a function of time. And so what that means is that these streamlines never change. They're always the same, and we're in steady state flow, so that makes sense. They are a function of x and y. And because they're a function of x and y, you can do a chain rule there. So you can do the partial of your stream function with respect to x times dx dt, and the partial of your stream function with respect to y, dy dt. And again, this would be dy dt and dphi dt, so this is going to be equal to 0. dx dt, that's the change in position with respect to time. Well, that's velocity. That's velocity in the x direction. And partial of y with respect to time is velocity in the y direction, uy. The next thing we do is we substitute in Darcy's law for velocity. So where you see ux, and you see uy, we now substitute Darcy's law in for ux and uy. So that's obviously k over viscosity, and then we've got the pressure gradient or potential gradient if we want to be more general. And so that's why we have substituted this dx dt for k over mu d phi dx, and then the same for dy dt. This is a d phi dy. Now, in order for this statement to be true, that the derivative of the stream function with respect to time is equal to 0, this term in parentheses must be equal to 0, and it must be equal to 0 all the time. It must be a general case, so for any value of x and for any value of y. Really, the only way that that could be true is if this d psi dx is equal to d phi dy, and this d psi dy is equal to minus d phi dx. Okay, you could flip the negative signs there, it wouldn't matter, but the point is that if this were true, if these two statements were true, then this term in parentheses would be 0 all the time. If we take the derivative, the second derivative, so the derivative of this, the first derivative is the second derivative. So the second derivative of our stream function psi with respect to x squared is the second derivative of potential with respect to, well, we took it with respect to x. So it's respect to x, and we already had a respect to y. So this is a second derivative, but in terms of x and y. And you can do the same thing over here. So the second derivative of psi with respect to y is the derivative of the first derivative. So you got to take this, take the derivative with respect to y, so you get a partial squared phi dx dy. And I believe this is where we finished up last time. So what you have now is we know that this term plus this term, you know, they're equal to each other, equal and opposite, so they must be equal to 0. Right? So this plus, this right here plus this is clearly 0 because they're exactly the same thing except one's got a negative sign in front of it. If this plus this is 0, then that means that this second derivative of our stream function with respect to x squared plus this second derivative of our stream function with respect to y squared must be equal to 0. And that's what I've written over here. As I said, that this is the second derivative of your stream function with respect to x squared plus the second derivative of y squared is equal to, with respect to x squared is equal to 0, and the reason is that these two things cancel. This is what's called Laplace's equation. It's a common equation in a lot of engineering, math, and physics type problems. Okay, and it applies for other physical phenomena, not just the stream function, lots and lots of other things. So it's a common mathematical problem. This is in Cartesian coordinates, obviously, because we have x and y. You could write it in cylindrical coordinates or spherical coordinates as well. And so if we want to do that and be more general, we would use our del operator. So del squared psi is equal to 0. If we did write it in cylindrical coordinates, it would be written this way. So del squared psi is equal to 0. We've already shown that in Cartesian coordinates. If it's true in Cartesian coordinates, it's going to be true in cylindrical coordinates as well. And so I could write the equation like this in terms of r and theta. Okay, so this is a partial differential equation. You've probably seen some of things like this in your transport phenomena class. And we can simplify this significantly because the stream function only is a function of theta. It's not a function of the radius r. And so what that means is that that whole term goes away. Now you're left with a much simpler partial differential equation. Okay, you can pull this r over here is equal to 0. Now you've got what's not a partial differential equation, but an ordinary differential equation. So the second derivative of your stream function with respect to theta squared is equal to 0. That's really easy to solve. Okay, you integrate once, you integrate twice, and what you get is a straight line, a linear relationship between the stream function and the angle theta. Now, we didn't give any boundary conditions yet, so you have two constants of integration, C1 and C2. These aren't the same constants of integration I had for my previous problems with potential. They're just new constants of integration that go in there. You need boundary conditions to determine those, and so we can apply those. I won't go through the detail much there, but it turns out C1 is your well rate times your viscosity divided by 2 pi times the permeability K divided by the thickness H. Okay, so this is my equation over here now. We still don't know C2, and again, like potential, you're going to need another piece of information to know that, but we might not necessarily need it. Recall that the angle theta is the inverse tangent of y over x. So now we're kind of going back into Cartesian coordinates. So here is my C1. I've replaced theta with the inverse tangent of y over x plus C2. That's for a single well. And like we did with potential and like we did for velocity, we could have multiple wells. And those wells could be interfering with each other. They could be multiple real wells. They could be real wells and image wells. But regardless, you can combine all that together and you get your stream function, which is given over here. And again, we still leave it in terms of the constant of integration C2, which we probably don't know, but that's okay. What we really want is relative value. So we might be comparing the potential, the stream function at one location versus another, in which case the value of C2 is not really important. So here are fluid and reservoir properties. Qi is, of course, the rate of the well. And now we've got this inverse tangent y minus yi and x minus xi. Okay. Streamlines started in injection wells and end at production wells. Right? They start where the fluid is being injected, and they're being produced somewhere else, and streamlines never intersect each other. So here's a picture of some stream functions. It's pretty obvious where the injector and producer well is. That might be a good homework or test problem in the future, is to identify the locations of the injector and producer. It's pretty simple here. Clearly, or at least you can tell that the two wells are here and here. Let's assume that the injector well is here and you have a producer well over here. So flow goes from the injector to the producer. Okay. There's really an infinite number of streamlines. We've only shown a finite number. The shortest distance would be a streamline that goes from here to here. It's not shown. But there's other distances that go along over here. Okay. You also have flow going in these directions, right? So it could go the other way. Here's another case, okay, and this is kind of an example. This is not all that different from, well, it's similar in some ways to problem number 2 in your homework, except we only have one real well here, whereas in the homework you had 2 real wells. But here's a case where, let's say I have an injector right here, and we have a sealing fault right here. And so this is an image well that's got the same injection rate. Well, if you're injecting, then fluid goes out from the injector, and it's kind of going out radially. But over here, it's affected by the fault. And again, mathematically, we describe that fault with the use of another injector well as its mirror image on the other side. And so what we have is that here at this the sealing fault, the streamlines come in, but they don't cross the streamline. They're interfered by its mirror image, so it sort of veers up like this. So the blue curves are the streamlines. The yellow is the isopotentials. Remember what isopotential means? It's a constant potential or constant pressure in the absence of gravity. And so they sort of look like circles, right? And if you only had one well and everything was isotropic, it would be a nice circle. But especially as you get further out, they start to get interfered by the other well. And so that's why you get these isopotentials that look like this. Next, I want to, and this is sort of a busy slide. Okay, I've got a lot on here, but what we have when we do reservoir engineering is we've got these different well patterns. And we don't always follow these exactly. Sometimes there's a little bit of randomness, or maybe that there's some geological reasons why we avoid certain locations. But ideally, we place our producer and injector wells in regular patterns. Okay. And I've listed a few of those. One of them is a 4-spot, which means you have 3 injectors and 1 producer. Okay, let's see if here's an example of a 4-spot right over here. So you've got 3, so the producer is the circle, and the injector is the triangle. So you've got 3 injectors and 1 producer. So it's kind of like making a triangle. Okay, and you've got this regular 4-spot. A 5-spot is maybe one of the most common, okay, and the one that we'll talk the most about. So a 5-spot is right here. Okay, I usually draw it as a square. They wrote it as a diamond. It's all depends on what angle you look at it at. But in a regular 5-spot, what you have is a producer in the center and injectors around the end. So you can think of it as a diamond or a square, and those injectors are at the corners of the square, and the producer is in the center. That's why we call it a 5 spot, because there's 5 total wells. 4 injectors, 1 producers. Now there's also what's called an inverted 5 spot. And an inverted 5 spot is the opposite of that. There's an injector in the center, and then there's producer wells on the outside. Okay, and all of these you've got, you know, a 7 spot, an inverted 7 spot, a 9 spot, an inverted 9 spot. Okay, and it all, you know, these all make sense, right? So you usually, so a 9 spot means there's 9 total wells, 1 producer, and then 8 injectors along the outside. There's another type of well pattern which we've kind of mentioned in passing a few times, and that's a direct line drive. That's almost like a one-dimensional flow. So in this case, this picture up here is a direct line drive. So we have injectors right over here, and we're injecting, and then we have producers right over here, and then maybe more injectors and maybe more producers. But it's direct line drive because it can go along a straight line. What I have here is called a peripheral flood. So in a peripheral flood, what you do is you've got injectors all along the edge, and you're injecting water along the edge, and you're producing along the center. So it's almost like you're trying to contain everything, go from the outside and push everything in. Now I would like to point out one thing. I'm going to go back to the 5 spot because that's what we're going to be talking about the most. And a 5 spot says that there's 4 injectors and 1 producer. And then what I had the next bullet is I have the number of injectors to the number of producers. The ratio is 1. So there's 1 injector for 1 producer. How on earth could that be? I just said in the first bullet that there's 4 injectors for every producer. So how could the ratio of injectors to producers be 1 to 1? Well, let's find out. Let's talk about a 5 spot pattern. What you have is a producer, and then maybe you've got something that looks like this, and you've got injectors. Okay, so you have 4 injectors and 1 producer. Seems like the ratio of injectors to producers would be 4 to 1. It's not, and here's why. Because it's adjacent to another 5 spot, these wells, and it's adjacent to another 5 spot over here. It's adjacent to another 5 spot over here. And then there's another one on top, obviously, right? So this well pattern right over here, this is 1 producer, but each of these injectors is being shared by 3 other, or 4 total, 5 spot patterns. So this well over here is only a quarter of a well. This is a quarter of a well, this is a quarter of a well, and this is a quarter of a well. Okay, so what we often do is do a model of just this particular 5 spot, and we call this a quarter 5 spot because each of these is a quarter of a well. It's a quarter of a well because the well is being shared by 4 different 5 spots. So 1 quarter plus 1 quarter plus 1 quarter plus 1 quarter is 1 injector, and you have 1 producer. So it's a ratio of 1 to 1. You can do modeling on this. Okay, you can create some equations and look at the streamlines and the velocity field and the potential field by doing this quarter 5 spot, but then doing image wells. Right? So you just do this, but you pretend there's an image well there, and an image well there, and an image well there, and an image well there. And if you really want to be accurate about it, this well needs an image well over here. This well needs an image well over here, etc. Oh, and then this well would need an image well somewhere else. You could go on forever. It could be an infinite number of image wells. That would be to be completely accurate. The truth is that you don't really need that much in order to be close to being accurate. Okay. Let me see if I have. Good. Yes, I have a figure that I wanted to show here. So this is a producer well, and then you got some injector wells over here. Oh, I'm sorry. I misspoke. Let me go back. So this is a 5 spot. What I really meant for a quarter 5 spot is that you do this right here. Okay, you do a quarter of the 5 spot. This and then ends up being a quarter of a producer well. This is still a quarter of an injector. This is a line of symmetry. This is a line of symmetry. Okay, so the quarter 5 spot is this corner, and you're just looking at that. So you would just model flow through there. So let me show what that is. So the big square on the outside is the 5 spot pattern. You got a producer in the middle and you've got injectors at the 4 corners. But the quarter 5 spot is this black box. Okay, and I'm only using a quarter of this well. This was always a quarter of a well in this corner, right? Because it was being shared by 3 other 5 spots. So you have a well here and a well here. You've got no well here and no well here. So if this is an injector, the fastest streamline is a straight line from the injector to producer, but then you've got other things over there, and then again these yellow lines are iso potentials. By the way, I made these plots. I coded them up. Okay, you could have done it in Python. I think I did it in MATLAB, using the equations that we developed last week and today with these stream functions, potentials, velocity fields. And I had to use some image wells on this. I just mentioned a minute ago that if I wanted to be completely accurate, I would probably have to use an infinite number of image wells, but I didn't do that. I think I only used 1 image well on each side, and that was close enough to giving us the correct answer. Sweep efficiency, aerial, we talked about sweep efficiency in 1 dimension. And remember when we talk about sweep efficiency, that's basically how good the water does at sweeping through and producing the oil. And even in 1D, we always left some oil behind, at least until you got to infinite time, right? So some oil is left behind. The same thing happens over here, and you can imagine that the oil that's along this path, the straight line path, gets picked up first, right? Because the shortest distance between 2 points is a line, and that's the fastest path. So any oil that's right over here gets picked up first. The oil over in these corners over here, they take longer to get up. And remember when we talk about sweep efficiency, displacement efficiency, and now aerial sweep efficiency, it's a time-dependent thing. If you wait long enough, then the sweep efficiency would be 1, but early on it's lower than that. Okay, and maybe I'll give my analogy again. Let's say you were trying to cut your grass in your backyard, and you were starting at one corner and going to the other corner, and you wanted to get to that other corner as soon as possible. Well, you would take your lawnmower and you do a direct line right over there, but the stuff in these corners over here wouldn't be cut yet. And you might have to go back through and do those, and those would take longer. It's sort of the same thing, is that, yeah, you're injecting all your water, at the same time, but it takes a lot longer for that water to pass through and push the oil through these corners than through the straight line. So that's what we refer to as aerial displacement efficiency, aerial sweep efficiency. And like displacement sweep efficiency, it's time dependent. So this is EA. It goes from 0 to 1, and it's a function of time. Like we learned before, up until breakthrough, it's a straight line. Okay, it's a one-to-one relationship. Every barrel of water you inject produces a barrel of oil. That's until you get breakthrough. Once breakthrough occurs, then you're producing water and oil, and that's true over here. Okay, that's true if the initial water saturation is equal to the residual water saturation. Now in the exam, I gave you a problem where the initial water saturation was a little bit greater than the residual water saturation, which means that some water was produced from the very beginning. The sweep efficiency depends on the mobility ratio. Okay, remember what we call mobility ratio. Mobility ratio, M, is the ratio of mobility. So it's KRW or mu W divided by KRO or mu O. So it's equal to that. So if your water is more viscous than oil, then your mobility ratio will be low. So, and if the viscosity, well, it also depends on the relative permeabilities, but if you've got a really viscous oil, like maybe, in Canada, then your mobility ratio is going to be very big. And maybe common sense alone would tell you that a low mobility ratio is good for production. It's really hard to inject low viscosity water and have it displace this high viscosity oil. So small m is high EA, large M is small displacement efficiency. That's true for the displacement efficiency as well as EA, the aerial sweep efficiency. So these are pictures. These were actual experiments that were done. And the top row has a mobility ratio of greater than 1. And the bottom one has a mobility ratio of less than 1. What you see here in this first plot is really early times. And you could see that when the mobility ratio is low, so the water is viscous compared to the oil, is that it's kind of doing this nice piston-like displacement. But when the mobility ratio is higher, it starts to deform, and it already looks like the water is going to get here faster than there. In fact, if you go to the first of the water breakthrough, this occurs in the top case when only 65% of the water has touched the oil, meaning that this white area over here is 35%. But when the mobility ratio is low, water breakthrough doesn't occur until 83%. So this has done a much better job of sweeping through that. What these other two are what's called the water-oil ratio. So it's the production well, that's the ratio of the water produced to the oil produced. You obviously want the water-oil ratio to be fairly small at the same sweep efficiency. You can see that over here that the water-oil ratio is about the same, but this occurs really early at 70%, whereas this doesn't occur until 87%. So the water-oil ratio doesn't get till 0.5 to 0.6 in the low mobility case until you've swept 87, 88%. And when the water-oil ratio gets a little bit bigger, this occurs at 82%, and this is almost 96%. So the big point here is that lower mobility ratio is better for your production. And we already knew that from 1D displacement efficiency, but it's true for aerial displacement efficiency as well, and will be true for vertical displacement efficiency. So that's always a problem for us if we've got a very viscous oil or poor meaning high mobility ratio. And so we have to come up with creative things to do that. Sometimes what we do is we try to reduce the viscosity of the oil by injecting heat or steam. Sometimes we try to increase the viscosity of the water by adding things like polymers. That's what enhanced oil recovery is. Thank you all, and have a good rest of the day.